like others breathe. So we left off talking about this famous, super famous identity, Euler's identity, the only one in our worksheet which we haven't proven. And incidentally, we will not prove. Unfortunately, I always try to explain where things come from, but unfortunately this one is way beyond the scope of our class. In fact, to get a little peek as to the reason behind this, you'd have to get to Calc 2 when you get to the second semester calculus, using these famous Taylor expansions. You can see some insight into exactly why this works the way it does. So last time we talked about some of the famous questions. What is E? Where does it come from? How to use it? And we took a big picture view where we said, you know what? If you have to explain it in a sentence, what Euler's identity does is it sets up this two bridges between some monomials, specifically monomials which are complex numbers in standard forms, and they can even be binomials or monomials. As long as they're anything in the complex plane, Euler sets up a bridge and says, hey, we can write it this way. And great things come from it. Unfortunately, we didn't see all the great things that come from it last time because we decided it was way too much for one lecture. So the idea was to just practice crossing the bridge and then leave some of the rest for today. Now, I'll remind you, crossing this bridge is really easy. All you do is find the R and the theta, which we had already practiced finding when we did the polar coordinates. That's exactly this R and this theta. You just plot this on the complex plane and you find the R and the theta. Sometimes you may have to use a formula. Sometimes it's common sense, like I, you know, it's 90 degrees, or -1, you know, it's 180. But something strange like 3, 2i, you find a tangent, you'd use a tan inverse to find a corresponding angle. And that's where we left off. In 2 seconds, that's a repeat and review of what we did last time. What we want to do is expand on that and explain exactly what's the big deal about this bridge. Why is this truly a better world than these other ones to begin with? So let me start off with this idea, multiplying. If we wanted to multiply a couple complex numbers written in standard form, these happen to be binomials, before Euler, here's what probably you would do. You would start to FOIL this and you'd say, alright, 3 times 1, that's 3, and then 2i plus 1, that's 2i, plus 6i plus 4i squared. The I squared becomes -1, so that's 3 plus 8i plus a -4. That becomes a total of -1 plus 8i. That's how you would do it before. Now we have a second option. Euler says, hey, we've got a much better idea. Here we've got an elegant way to do it. What you do is you cross this bridge over to Happy Land and you say, you know what, we're going to write these as Euler numbers. And to write these numbers as Euler numbers, keep in mind you find the R and the theta. This is 3, this is 2, so this would be equal to, I think we've done this before, it would be the square root of 13, the square root of 13 e to the I, and what is the, I need a tan inverse. This is not a famous angle, so I need to find the tan inverse. Let's do that. The little magic number machine. Tan inverse of 2/3, that's 33.7, so that's 33.7 degrees approximately, times 1 plus 2i. To find that one, you go 1 over 2, so this will be the square root of 5, and then tan inverse of 2 over 1. So I'm going to clear all this, and I'm going to do tan inverse. The opposite is 2, adjacent is 1, so the ratio is, let's do it correctly, 2 over 1, just so you see how we calculated that, 63.4. So this would be, so for this one right here, the angle is 63.4 degrees, and the R is equal to the square root of 5. So therefore this would be the square root of 5e to the I times 63.4 degrees. So over here, Euler would say, hey, to multiply these, all you do is multiply the coefficients together. So it would be the square root of 5 times 13, that's 65, times e raised to the... How do you multiply numbers that have the same base? Well, when you multiply numbers that have the same base, all you do is add the exponents. So this would be 97.1 degrees. That's how you would do it in Euler world. Okay? And this is a non-famous example. For famous examples, it works just as nicely. Try a famous example. Alright, let's try some famous ones. This is a famous one because the angle, I know if you go over to the right 1/2 and up square root of 3 over 2, that's the famous triangle. This is 1/2 square root of 3 over 2. So this must be 60 degrees. R is equal to 1 in this case. So that's why I'm calling these famous. This one over here would be a similar one, but for 30 degrees. The opposite is 1/2, the adjacent one square root of 3 over 2, and that's 1. So anyways, here's how multiplying works. In the regular world, in the mundane world, you would start foiling this. You'd say 1/2 times that would be the square root of 3 over 4, plus the insides would be 3 over 4i, plus the outsides would be 1/4 I, plus the last ones. That would be square root of 3 over 4i squared. Now the I squared becomes -1, square root of 3 over 4. That becomes negative square root of 3 over 4, and a positive 1. These guys go, and that leaves you with 3/4 I plus 1/4 I for a total of 1i. Right? In the Euler world, says Euler, take this bridge, come with me to the Euler world. This one becomes e to the 60 degrees I times e to the 30 degrees I. And to multiply these two numbers, whenever you've multiplied two numbers that have the same base, all you do is add the exponents. So 30 i's plus 60 i's. How much is 30 i's plus 60 i's? Whether you use your calculator on that one, that's 90 i's. And so this was how Euler would do it. Incidentally, we use the Euler identity. This one, e to the I theta. If you have e to the I 90 degrees, that becomes cosine 90 degrees plus I sine of 90 degrees. And what does that become? Cosine 90 degrees, that becomes, here's the cosine graph. Cosine of that is 0. Plus I 90 degrees, that becomes 1i. So this becomes a total of I. And so this becomes famous one right here. This becomes 0 plus I times 1, which is equal to I as expected. I just did this part to check, double check what was expected. You see that? Nice. Multiplying in this world is a bunch of foiling stuff. Multiplying in this world is just adding exponents. That's why it's so nice. It gets even better than that. Try dividing now. Now suppose you wanted to divide. Let's just say we wanted to divide this number by that number. If you were doing the old style, you would multiply top and bottom by the conjugate. You would go 3 plus 2i over 1 plus 2i is the same as that times 3 that times 1 minus 2i multiplied on top and 1 minus 2i multiplied on the bottom, and so on and so forth. Euler has different ideas. Euler says if you want to divide two numbers, if they're monomials, and you have, especially if parts of it have the same base, various exponents, all you do is subtract the exponents. So Euler would say this is just the square root of 13 over 5. 13 over 5 times e, and then you would subtract the exponent. So 33.7, take away 63.4. That's 33.7 minus 63.4. That's approximately 29.7 degrees negative. That's it. As easy as it sounds, that's all you got to do for Euler. So this would be square root of 13 over 5 times cosine of negative 29.7 degrees plus I times sine of negative 29.7 degrees. And you can calculate those if you want. This seems like a fun exercise. Calculate this whole thing and distribute that, and you should get exactly the same answer as doing it this way. I'll let you work on that. Incidentally, a lot of people abbreviate this cosine of the angle plus I times the angle. Often people will abbreviate it like this. Just so you know, often people will abbreviate like this: CIS theta, which means cosine of the angle plus I sine of the angle. This is just short for this whole thing. Just so you know, everybody does. Some people do it. Anyways, dividing non-famous numbers, there's totally different flavor. Here you got to do conjugate stuff. Here just subtracting the exponent, just like that. Let's do another dividing one, but this time let's do some famous ones. So this one, again, if you were to divide that but divided by that, you'd have to multiply top and bottom by the conjugate. You'd have to go 1 over 2 plus the square root of 3 over 2i divided by the square root of 3 over 2 plus 1/2 I. Multiply top and bottom by the conjugate on the bottom, so you'd go square root of 3 over 2 minus 1/2 I, square root of 3 over 2 minus 1/2 I, and then clean it up, and you'd get the right answer. Euler proposes a different idea. If you've got e to some angle and e to some angle and they're being divided, all you do is subtract them. So 60 i's take away 30 i's, that becomes 30 i's. And that's it. You're done. In Euler world, you're done. Dividing monomials is really easy. Dividing numbers that are written with the same base is really easy. In the Euler world, all you do is subtract the exponents. So you subtract the bottom exponent from the top. And you could convert back again using the identity. You could say this is cosine of 30 degrees plus I sine of 30 degrees and compute that, and that would take you back to the regular world standard form. Okay? But wait, there's more. I should make an infomercial on Euler identity. Not only can you multiply and divide in a much easier way, but wait, there's more. Imagine taking the power of this complex number written in standard form. On a regular day, you would probably have to try to do something like this: 3 plus 2i, and then maybe square that. I don't know. You'd have to do that times itself 10 times. So there's many ways to do it. You could square it and then do that 5 times, or you'd have to expand that using the binomial expansion theorem, or you'd have to do it by one where you FOIL it. Anyways, no matter how you look at it, it doesn't look like a particularly fun problem to do or elegant. This looks like a lot of grunt work. Euler proposes something much more elegant. Euler says, hey, this is much easier. In the Euler world, here's what you would do. You would change this to the Euler form, which we agreed was the square root of 13 times e to the I think it was 33.7 degrees. If not, don't worry about it. Just let that slide. It's close enough. Euler proposes, hey, this is a different kind of problem than this one. This is a binomial, so to take that to 10th, you have to expand that and FOIL. Here, this is a monomial. To take that to the 10th, it's a million times easier. All you do is take the square root of 3 to the 10th power times e to the I. This is power to power. This would be 337 degrees. And you're done. This would be 13 to the 5th power, following your algebra rules, because this is 13 to the half times 10 is 5, times a cosine of 337 degrees plus I times sine of 337 degrees. and that would take you back to the other world, and you're done. Just like that. This is amazingly elegant. You take the 10th power of this, so easy. Over here, it's a totally different world. Okay? I told you. Euler's big. Big time. He was a real deal. Okay? And you can even do it on some famous ones. Let's take this one, for example, the 10th power. This is the one where you go over 1/2 and up square root of 3 over 2. So this is the medium one, famous one. This is 60 degrees. And this is 1. So therefore this is equal to, Euler would say this is equal to e to the 60 degrees times I. And raising it to the 10th over here is a piece of cake. E to the 600 degrees I. And that's a piece of cake. That's cosine of 600 degrees plus I times sine of 600 degrees. I told you. If you compute that, that will take you back to the standard world. Okay? Here, I'll compute it this for fun. If you go all the way around, that's 300. If you go all the way around, that's 360 plus 360. That's 720. Whoa, we gone too much. If you go 720, we got to go back, take away 120. So this would take away 120. That would put you 60 short. The reference triangle would look like this. This is 1. This is 60 degrees. So this is 30 degrees. So this is 1/2 square root of 3 over 2. Negative, negative. So cosine would be negative 1/2 minus square root of 3 over 2 I. That's what it would equal to. I told you. With great elegance, taken to the 10th power. No problem. But wait, there's more. Let's run down through my infomercial. Cheat sheet here. Multiplying, easy. Dividing, easy. Powers, easy. How about roots? What does Euler's identity tell us about roots? Well, let me tell you. Take, for example, this number, the square root of I. Have you ever wondered what is the number that when you square it, you get I? And you might think, hey, maybe that number is I itself. But wait, if I square I get negative 1. So that doesn't help. Then you think, hey, maybe this negative 1. But when you square it, you get 1. So that doesn't help. You want something that when you square it, you get I. What is the number that when you square it, you get I? This is a difficult problem in this world. In the world of monomials, even if it's a complex number, it's a difficult problem. How do you figure out the square root of negative I? But if we just cross the bridge and come over to the promised land, to Euler land, becomes a piece of cake. Let me tell you what I mean by that. For roots, here it is. I can be written as, you can either do the old-fashioned way, or you can just imagine it on the complex graph. What is the angle here? If it's a famous one like this one, I can figure out it's 90 degrees. And this R is equal to 1, so it's equal to 1 times E 90 degrees I. Right? Stop me if I'm lying. This is the regular world, monomial world. This is Euler world. Exponents, powers of E. Regular world, Euler world. Now, over here, the Euler world is hard, but over here, E to the 90 degrees I, oh, it's a piece of cake. This is just the square root of that. So you could take E to the 90 degrees I and raise that to the 1/2. Distribute that, that becomes E to the 45 degrees I. Stop me if I'm lying. Which becomes cosine of 45 degrees plus I times sine of 45 degrees. I can't slow down. This becomes the square root of 2 over 2 plus I times the square root of 2 over 2. I know those because they're famous. And there you go. The square root of I is square root of 2 over 2 plus I squared of 2 over 2. If you don't believe me, try it. Here's what would be the ultimate test. If you take the square root of 2 over 2 plus square root of 2 over 2i and you square it, you should get, well, you could get some stuff and simplify, but ultimately you should get I. Try it. If you follow this, you get the square root of 2 over 2 squared plus 2 times the square root of 2 over 2 times the square root of 2 over 2i plus the square root of 2 over 2i quantity squared. That's just foiling that. First one, last one, the 2 times the inner ones. This becomes 2 over 4. This becomes, well, I can cancel those. That becomes 2 over 2i. And this becomes 2 over 4i squared. But wait a minute, what is I squared? I squared is negative 1, so this becomes 2 over 4 plus I, that's 2 over 2 is 1. I squared is negative 1, so it becomes negative 2 over 4. Oh no, we didn't. 2 over 4, negative 2 over 4, that's gone. I told you. See why they pay me? Told you. A number that when we square it, you get I. Not only that, but you know, there's more. You could easily find the cubic root of I. In this rule, it might be hard, but if you think about it this way, 90 degrees I, do you know how easy it is to find the third power of that? All you do is multiply the powers, and you're done. So, again, let's go back to our little thing here. What is the Euler's identity good for? It makes multiplying totally easy, dividing a piece of cake, powers a piece of cake. It helps us find roots that we never even hoped to find before. But wait, there's more. Let me tell you the fundamental theorem of algebra story. Okay? Fundamental theorem of algebra. The fundamental theorem of algebra tells you basically if you've got a polynomial equation such as this one, 3x squared plus 5x plus 7 is equal to 0. This is a polynomial equation of degree 2. The number of solutions is equal to the degree. This is degree 2, so there are exactly 2 solutions to this polynomial equation. It generalizes that. It says if the polynomial equation was degree 3, there would be exactly 3 solutions. If it was degree 4, there would be exactly 4 solutions, and so on and so forth. Super famous fundamental theorem of algebra. Gauss proved it. Gauss, as they call him the Prince of Mathematics. That was his PhD thesis at the age of 17. Anyways, this is not Gauss's party, so I'll let that slide. But Gauss proved the fundamental theorem of algebra. The degree of the equation is equal to the number of solutions. So let's see what would Euler say about that. Okay, what does Euler's identity say about that? Well, apparently at first it seems like nothing, but then you start to dig into it and you start to see some amazing patterns. Let's see if we can see those amazing patterns. This equation, x equals 1. What's the degree for that equation? The degree is 1. Therefore, fundamental theorem of algebra would say that has one solution. What is it? Well, you're looking at it. X equals 1. That was easy. What about x squared is equal to 1? What's the degree for that equation? Degree 2. According to the fundamental theorem of algebra, how many solutions should it have? 2. Where are they? Well, you could say x squared minus 1 is equal to 0. Then you could say x minus 1 times x plus 1 is equal to 0. Therefore, x equals 1 or x equals negative 1. So there are your 2 solutions. I told you, 2 solutions, degree 2 equation. No problem there. What about degree 3? x to the third is equal to 1. Degree 3. Degree 3. According to the fundamental theorem of algebra, how many solutions do you have for this equation? You have exactly 3 solutions. What are they? Well, you could find them this way. X to the third minus 1 is equal to 0. Therefore, x minus 1 times x squared plus x plus 1 is equal to 0. This is a famous factorization, by the way. Difference of cubes. You should all know how to factor that. If not, may I recommend MathHands, the algebra version? Alright, you should know how to do this, and then you got something times something equals 0, so x minus 1 is equal to 0, x squared plus x plus 1 is equal to 0. So this one you could solve easily, x equals 1. This one you could solve easily by using quadratic formula. Negative 1 plus or minus the square root of negative 3 all over 2. I know I did that really fast. Sorry, I can't help it. X equals negative 1 plus or minus I times the square root of 3 all over 2. There you go. Count the solutions. How many solutions do you see here? 1, 2, and 3. You got 2 of them here. 1 for the plus and 1 for the minus. So you got 2 of them here, 1 here, a total of 3 solutions. What was the degree here? 3. I told you. That's why they pay me insane amounts of money. Degree 3 means 3 solutions. Degree 4, x to the fourth is equal to 1. According to the fundamental theorem of algebra, how many solutions would you expect? You would expect exactly 4 solutions. What are they? Well, fortunately, you've got the skills to solve them already. X squared minus 1 times x squared plus 1 is equal to 0. X minus 1 times x plus 1 times x squared plus 1 is equal to 0. Therefore, x equals 1, x equals negative 1, x squared plus 1 is equal to 0. So x squared is equal to negative 1. So x equals plus or minus I. How many solutions have you got here? 1, 2, 3, 4. 4 solutions. I told you. It's a nice pattern, huh? And so on and so forth. Now, apparently, this still doesn't tell you exactly my point. I haven't told you the punchline here. Exactly, what does that have to do with the beautiful, the most powerful, most elegant identity that humans have ever created? Not humans, only the man that could calculate this like others breathe. My buddy Euler. What is the connection between this and the fundamental theorem of algebra and the roots of unity? These are all called roots of unity. These are the 4th roots of unity. These are the cubic roots of unity. These are the squared roots of unity, etc. What's the connection? Well, here's the connection. The connection still doesn't seem apparent, but you start to get at it when you start to plot these excuse me, on the complex plane. Let me start to plot these. For x equals 1, here is the solution. No. Hold on. Can't rush perfection. X to the third is equal to 1. X to the fourth is equal to 1. Now I'm going to leave some space here to see if you guys can guess the x to the 5 is equal to 1. Alright, what were the solutions for x squared equals 1? Just x equals 1. Where can you plot that? Well, you could plot that right around here. There's the x equals 1 solution. X equals 1. Check. Can you see the pattern yet? No, of course not. How about for this one? Where are the solutions for this? The solutions were 1 and negative 1. Remember? You remember 1 and negative 1. Those were the solutions for that one. Where are they on the graph? Well, one is here, 1, and the other one is there, negative 1. Can you see the pattern? Say no. How about x to the third? What are the solutions for x to the third? They were 1, negative 1/2 plus 1/2 square root of 3i, or negative 1/2 minus I square root of 3 over 2. Where are they on the complex plane? Well, here's one. The other one was negative 1/2 and square root of 3 over 2i. That would be somewhere over here. Negative 1/2 plus the square root of 3 over 2i. The other one was negative 1/2 minus negative 1/2 minus square root of 3 over 2i. That's the other one. Can you see the pattern yet? Maybe, maybe not. In fact, the pattern becomes much more clear if you put these on a unit circle. There's the one circle. There's this circle cut in half into 2 pieces. Here's this circle cut into how many pieces? No. Oh no, we didn't. Well, yes, we did. We cut it up into 3 equal pieces, 120 degrees apart. This one, oh no, what were the solutions for this one? I, negative I, 1, and negative 1. Where are they on the graph? 1, negative 1, I, negative I. Whoa, no, we didn't. Where are the solutions here? The solutions occur on the unit circle, equally spaced, cut into 4 pieces. Boom, boom, boom. Those are the 4 solutions. This one was unit circle cut into 3 pieces. This one was the unit circle cut into 2 pieces. This one was the unit circle uncut, just left as 1 piece. Do you see the pattern now? How do you like me now, huh? I told you. But wait, there's more. If it was x to the 5th is equal to 1, and you were asked to find all the roots of this polynomial, which are called the 5th roots of unity, and you had to guess based on this pattern, and you just had to take a wild guess, how would you begin to guess? You guessed it correctly. The first one would be at 1. The other ones would be equally spaced around the unit circle, 360 degrees. If you can eat 5 spaces equally spaced, each one comes out to 72 degrees. So the next one would be at 72 degrees. So this would be EI to the 72 degrees, which you could also write as cosine 72 degrees plus I sine of 72 degrees. Next one would be right here at I 144 degrees, E to that. Next one would be that plus 72 degrees. The next one would be there plus 72 degrees. Next one would be back here, which will repeat it up to 360. And there you'd have your five roots of unity equally spaced on the unit circle. Isn't that amazing? I thought it was amazing. 210, 216. Next one would be that plus 72. That would be 288. 288 degrees I, where that's the power of E. And then this one will get you back to 360. So which is the same thing as 0 degrees. So you wouldn't get anything new, you'd get the same roots. That's the pretty amazing pattern for the roots of unity. But wait, there's more. What does that have to do with Euler's identity? With the man that could calculate like others breathe? Well, you might be wondering, okay, that's nice, a pattern, but where does it come from? It comes from exactly Euler's identity. Let me take this one, for example, and break it down using Euler's identity to help you see. This will shed some light into the issue, I think. If suppose you wanted to find x to the 4th is equal to 1, and you had no idea what it is, and you say, you know what, I have no clue what x is. X, I don't know. Who knows? Je ne sais quoi. You say to yourself, you know what, I don't know what x is, but I know whatever x is, I can write it as e to the I theta. Assume you know that the r is 1, because it has to be a root of unity. Just let that slide for now. or. So then we substitute this in here and we say, all right, e to the I theta to the fourth power is equal to 1. And not only that, but the 1 can also be written in the Euler world. Let's move everything in the Euler world. 1 is the same thing as e to the 0 degrees, right? It actually, more than that, it could be e to the 360 degrees, you agree? Or it could even be e to the 720 degrees. In fact, it could be e to the any multiple of 360 degrees. Yes? So I could rewrite this as e to the I 4 theta is equal to e to the any multiple of 360 degrees, any integer multiple of 360 degrees. How is it that, times I forgot the I. Sorry. How is it that this e raised to this power can be the same as this e raised to that power? How? Well, for sure they would be the same if these were equal to each other. If 4 theta I is equal to k 360 I, then this would be true, then that would be true, then that would be true, then that would be true. So this would mean that if I solve for theta, theta is equal to, cross out the i's, any multiple of 360 degrees divided by 4. So theta is equal to any multiple of 90 degrees. So this is telling me that if theta is any multiple of 90 degrees, x will satisfy this equation. So that means x is equal to e I, my theta here, I'll substitute it in here, k times 90 degrees. That would mean that that would mean that, for example, if you take k equals 0, that means e to the 0 I, comma, if you take k equals 1, e to the I 90 degrees, comma, e to the k is equal to 2, e to the I 180 degrees, and e to the I 270 degrees, and e to the 360, but then it repeats itself. There you go. I found 4 solutions to the equation, and the fundamental theorem of algebra says that's all there is. There aren't any more. So this is a way to shed light into exactly why the root